All right, so now we're going to talk about Lewis structures real quick. This is sort of our beginning point for drawing molecules here. So first, like, what is a Lewis structure? Here's an example down here, just so you sort of know what we're talking about. But these are 2D representations of molecules. They show the connectivity of atoms and the distribution of electrons. A line represents a bond. Well, that's not good. Let's do this. A line represents a bond, so that's sharing of 2 electrons. So this represents electrons being shared between a carbon and a hydrogen. And then the lone pairs are represented by dots of atoms. That's not what that should say. Oh, dots on atoms. Okay, great. Yeah, they're represented as dots on atoms. So what that represents is an orbital that contains a pair of electrons, but it's not a bonding pair. So this is what a Lewis structure represents: distribution of electrons, connectivity of atoms. What it doesn't show you is the shape of the molecule. This is something that's really important to understand. Molecules are 3-dimensional. We have to understand their geometry in terms of a 3-dimensional shape. Lewis structures are great. We talk a lot in terms of these types of structures, but they are 2D projections. They're not the actual shape of the molecule. One example, just on the screen right here, is this is a perfectly valid Lewis structure for water. Water is not a straight line. Water is what we consider to be a bent shape, okay? So this is what we're going to be sort of building towards here. The first thing we got to do, though, before we can talk about molecular geometry, is figure out how to build these Lewis structures. Okay, so here are the rules for drawing Lewis structures. And this is going to be starting with a molecular formula of sorts, all right? So the various steps are you arrange the atoms, you got to add up the total number of valence electrons, connect those with single bonds, complete the octet of all the constituent atoms, any extra electrons go in the middle, and then check if everybody's happy, okay? So those are the rules. I think it's gonna make a lot more sense to see them while I'm doing an example. But this is this page in your notes that you can have in front of you, so that in like one slide when I do the example, you can follow along. It's really not that bad of a process though, because we're sticking with organic molecules. When phosphorus or sulfur is the central atoms, things can get a little hairy, things get a little weird. That's not going to be the case here, because we're sticking with row 2. It always sticks to that octet rule, where it just wants the full valence shell, meaning, again, carbon will have 4 bonds, nitrogen will have 3 bonds, carbon will have 4 bonds, nitrogen 3 bonds, oxygen 2 bonds, and the halogens or hydrogen will have 1 bond. Okay, also just to sort of put in these missing electron pairs. All right, so let's do some examples of, come on. There we go. Some Lewis structures here, okay? So first step is, I actually do step 2 first. Add up the number of valence electrons. So remember this last video, we were talking about valence electrons and being able to figure out how many each element has. So carbon, by looking at the periodic table, we can tell it has 4. Hydrogen has 1. So that gives us a total of 8 valence electrons in this, what is a methane molecule. I'm going to use the names of these compounds, these organic molecules, that might not be familiar to you yet. That's okay. Don't think that you have to know them. There will be a time when you do. But nonetheless, I think it's just good to start hearing the vocabulary. So I want to make sure to use that. Again, this is methane. All right, so I'm going to put the least electronegative atom in the middle. That's actually hydrogen. But hydrogen can never have more than 1 bond. So we know it's not going to go in the middle. So in this case, it's carbon. And then I'm going to decorate it with those constituent atoms. Then you want to draw in single bonds. And then for each bond that you laid down, you're going to have to subtract 2 valence electrons, right? So it's like, this is how many electrons you have to use up in your drawing. Each time you lay a bond, you've laid down 2 of your electrons. So at this point, I've laid down 2, 4, 6, 8. So that means that I have used up all of my valence electrons. So I can't add any more to the board, all right? The next thing you do is you go through and you make sure that everybody is happy. How many electrons does hydrogen like to have in its full valence shell? 2. And each hydrogen does indeed, let me use this. Each hydrogen does indeed have 2 electrons that are being shared in that bond, right? That's what that stick is representing. Likewise, how many valence electrons does carbon like to have in its full shell? Should have said 8. And so indeed, between all 4 of these single bonds, that is 8 electrons being shared with carbon. Okay, cool. So then what that tells us is that this is indeed the legit Lewis structure for methane. Once you've checked out that everybody's happy, that's how you know you're good. Okay, so now let's do a slightly more complicated example. This is sort of best case scenario where in the first go, you've laid down everything and you're done. So now we have nitrogen trichloride. We got to figure out how many valence electrons are in there. Everybody pause this video and take a second to figure that out. Let me do it actually too. Okay, so then we're going to lay the less electronegative in the middle. Decorate it with the chlorines on the outside. Again, sort of placement doesn't matter. If you had one up top, that would be the same thing. And then you're going to put down single bonds, connect everything to that central atom. How many electrons did we just lay down on the board? Should have said 6. All right, so that's 2, 4, 6 electrons down on the board. So then we got to subtract those from our valence electron total. That gives us 20. That means we got 20 more electrons. We have to figure out where they go. So now this is going to be different. We've got a little bit more complicated situation than we did with methane. So what do you do with these leftover electrons? First thing you do is complete the octet of all of the constituent atoms, the ones along the outside. So how many does chlorine need? Currently it has 2 from that single bond. So that means it needs 1, 2, 3, 4, 5, 6 to make its full octet. Likewise, same this guy, same with that. All right, so then that accounts for another 18 valence electrons that are down. Okay, so now I got 2 left. Where do they go? If all of your constituent atoms have a full octet, the extra electrons go in the middle. That accounts for those 2, so now I got 0. And then the last step, make sure that you got to check to make sure that everybody's happy. Nitrogen wants 8, currently it has 2, 4, 6, and then that lone pair being 8. Likewise, each of our chlorines want 8, 2, 4, 6, and then that bond makes 8. All right, so then the last example is going to be sort of the last level of complication that can occur. We're going to start by putting the less electronegative in the middle, decorating it with the constituent atoms. One thing I didn't do, got to make sure to do, is to add up the total number of valence electrons. Again, practice this before I figure it out. Okay, then you're going to connect to the central atom with single bonds. How many electrons did that account for? Then you're going to go put these 12 valence electrons that I have left over. They have to go to complete the octet of the constituent atoms. All right, that's the next rule. But now I got all my electrons down, so that makes 12. But now I have a new problem. I got all my electrons down on the board, so I can't add anything else. But carbon only has 2 4 electrons associated with it at this point. So it does not have that complete octet. It is not happy. So since I can't lay any more electrons down, what I got to do is move them around within the structure that I've already built. So what I'm going to do is I'm going to take these 2 electrons from oxygen and turn them into a bond, right? I didn't change the number of electrons that were down. All I did was move it from being a lone pair to a bond. Oxygen's still happy because it has 2, 4, 6, 8 electrons associated with it. But now carbon's gained another pair. And so that's the game that we have to play over here as well. Take that lone pair away and make it another bond. Okay, and this is now, so this represents a double bond, or as we said before, the sharing of 4 electrons. And so this is the correct Lewis structure for carbon dioxide. You can go back and check, double check, make sure everything does have its happy octet and all the electrons are laid down. Now, if you were sort of clever, you might say, okay, well, let's get to this same problem that I had before. Why can't I just have taken this pair of electrons, moved it down there, but then also taken this pair from the same oxygen and done it like that, right? This is not the correct Lewis structure for carbon dioxide, but why? Everybody has a complete octet. You can go through and prove it. The reason is because this structure has a formal charge associated with both this oxygen over here and this oxygen over here. So let's talk about what a formal charge is. A formal charge is essentially a measure of how many electrons are sitting around a particular atom. This oxygen here, you can see with its 3 lone pairs, has a lot more electrons sitting on it than this oxygen over here. It has 1 lone pair, but the other 6 electrons aren't bond. It's being shared, so it's not sitting directly on the oxygen. Okay, so this is this measure of formal charge. So let's get to how to calculate that real quick. So for this red one, so what we do to calculate formal charge is stated here. So you take the number of, formal charge, you take the number of valence electrons that the atom should have, that oxygen has when it's all by itself, and you subtract the number of, damn it, that should be associated with the atom valence solution. All right, so let's do this red one. So what you're going to do is you're going to take the number of electrons that are currently associated with this atom, and what I mean by that is it has 1, 2, 3, 4, 5, 6 electrons in lone pairs, but then also you're going to count this electron in the bond as well. So you only count, when you're doing a formal charge calculation, you only count 1 electron from each bond, okay? So this is 7 electrons are associated with this red oxygen atom. And then to calculate the formal charge, you're going to subtract the number of valence electrons that the atom normally has when it's all by itself. So oxygen has 6 valence electrons. God damn it. All right, so let's start with this red oxygen here. To calculate formal charge, you're going to take the number of valence electrons that the atom has when it's all by itself. So how many valence electrons does an oxygen atom have when it's all by itself? Again, we find this by looking at the periodic table and counting the columns. There are 6. And then we're going to subtract from that the number of electrons that are currently associated with this molecule. And what do I mean by that? So what I'm going to do is I'm going to count all of the lone pair electrons. Let's do this. So that's 1, 2, 3, 4, 5, 6 electrons associated with this atom in terms of lone pairs, and then 7 from my covalent bond. So when we're calculating formal charge, we're only going to count 1 electron from each covalent bond. So I'm going to take my 6 and subtract 7. So again, the 6 number of valence electrons oxygen has when it's all by itself. The 7, how many it has in your actual structure. So this is how you get a formal charge of -1 associated with that red oxygen. And likewise, we can go over here and repeat this calculation for now my blue oxygen. My formal charge is going to equal, again, just the number of valence electrons oxygen has when it's all by itself, so 6. And then the number that are currently associated with that blue oxygen. So take a second and count that. We got 1, 2 from lone pairs. And then again, each bond's just going to count 1. So that's 3, 4, 5. So this is how I get a formal charge of +1. Okay, so atoms don't like to have formal charge. There are certain circumstances where that charge can be stabilized, so it's not like we're never going to see it, but generally speaking, holding a charge is higher energy than having it be evenly distributed, right? So that is why this would be an incorrect structure for carbon dioxide, and the correct one would have that more equal share of electrons. So if there's ever a possibility between drawing a Lewis structure with a formal charge and then a way to do it without a formal charge, you know that the 0 formal charge way is going to be the correct way. And again, these rules, if you stick to these rules here, you will always have a 0 formal charge. Okay? Cool. So now we got to talk about electronic structure in atoms. First, take that quiz or whatever it is for the Lewis structures. Make sure to practice.